So in the last video, I left you very suspenseful, wondering what would happen if we rolled 5 dice instead of just 1. Well, let's go ahead and look at what happens. So here's our graph of the data. But again, remember, still 3,000 people, each rolling out 5 dice, but each person just winning the mean amount of money. We have our mean, our median, our standard deviation. You probably notice what's similar and what's different than before. But let's sort of talk about why some of the things happened. So why does my data look so different than what I had here? Well, before, when you rolled just a single die, how did you win $1? You rolled a 1. That was it. Right? You were just as likely to roll a 1 as a 3, as a 6, right? They were all the same. But now, how would you win $1? Imagine that you're rolling those 5 dice. The only way that you're going to win $1 is if all 5 dice are a 1. Or basically you're getting a Yahtzee in ones to begin with. That's not very likely to happen. Same idea with winning $6. The only way that's going to happen is that you're going to have to roll all 5 6s. So what we're seeing now is when we have that mean being calculated, we have a lot more people in the middle and a lot fewer people in the extremes. And hopefully that makes some intuitive sense. We saw the mean changed a little bit, and the median did as well, but they're not drastically different. What we saw, though, is that our standard deviation did get smaller. Because that's what we're seeing, is those extremes aren't happening as often. So that's why that standard deviation went down, because more data is close to the mean and less data is far from the mean. So let's go through and summarize that in the same way that we did before. So now looking at the data, what kind of shape would you say this has? Well, now it looks like it has one peak, so it's unimodal. It also looks pretty symmetric, not perfect, but pretty symmetric. Mean and median are pretty close to sort of help me confirm that. And then we don't really have any outliers, nothing really stands out. Standard deviation, let's go ahead and do that math so we can go through here as well. So this time my mean is 350 to 2 decimal places, going over our standard deviation of 77 cents will give me 273 and 427. So now when looking at the amount of money won, by our 3,000 people, this time we described the data as being unimodal. And pretty symmetric. Still, though, with no outliers. This time, the mean amount won was $3.50, with again our half or 50%, winning $3.60 or more. So there's our center taken care of. And then finally our typical person won between our $2.73 and $4.27 that we had over here, which is roughly about, let's see, here and here. So again, typical person, not everybody. So imagine what would happen now if instead we rolled 10 dice and you got the average or the mean of the 10 dice. What would you expect to have happen? Well, hopefully we would think that the extreme values are even less likely to happen now. I mean, getting all 10 dice to be a 1 is going to be very, very unlikely to happen. And we're going to have a lot more people toward this middle. So here is what happened. We see the same idea happen. So very few extreme values. We're kind of crunching in here, much closer together. Have our mean and median didn't change a lot, changed a little bit. Standard deviation went down. But again, what we're seeing for that visually is because these values here on the extremes are not happening near as often. That data is getting closer together, which means my standard deviation is getting smaller. So what I'd like you to try to do here is pause the video, write the same type of paragraph we have up here, and then play the video to see if your answers match. So let's see how you did. So again, I described this shape as being unimodal and pretty symmetric. Again, I don't see any extreme outliers to be worried about. Our mean, rounded to 2 decimals, would be $3.50. The median is as well, so also half of people won $3.50 or more. Doing our calculation over here for standard deviation, being about 53 cents, gives me $2.97 and $4.03. So our typical person won between $2.97 and $4.03. All right, so now tying all of this together, let's talk about what happened as we changed things. So we started with rolling a single die and got some data. We then rolled 5 dice and got some data. And finally rolled 10 dice and got some data. And we saw some changes, but not everything changed. So let's try summarizing what hopefully we saw. So what did we notice? And more specifically, what did we notice as we rolled more dice? And when we're rolling more dice, we're increasing our sample size. So what happened as we rolled more dice? Well, first, the shape of our graph did change. So that our shape started as uniform. It did not have any peaks. But became not only unimodal, but unimodal and symmetric. And so hopefully, see, if I were to actually put a picture on that, like a nice little curve, that really looks like our normal distribution that we've drawn a lot. So it very much became normal looking as we sampled larger samples. Our center, which was the mean and median, kind of hovered right around that 350-ish mark for pretty much the most part. So the center didn't really change. What we did see a big change in was that standard deviation. So as we rolled more dice, the standard deviation got smaller, which means that our data is getting closer together. So our means are getting closer together when we take a bigger sample. The last part on this page is just kind of reminders of some symbols, because you're going to see them showing up quite a bit. So remember, we have different symbols for sample values versus population values. So again, just make sure yourself is familiar with the symbols as we dive into formalizing our sampling distribution.